Assalamu alaikum. Today we shall talk about quantum harmonic oscillator. Harmonic oscillator is a topic that is discussed in every branches of physics, and it is very important, and there are lots of things that we can learn from harmonic oscillator. In quantum mechanics, it introduces or using the harmonic oscillator, we teach several mathematical techniques which can be used to solve complicated systems. Now, to give an example of harmonic oscillator, a spring oscillating, a spring hanged with a mass hanged in a spring, and its oscillation is simple harmonic. So the harmonic oscillator has potential energy, which is half k x square, and it has the kinetic energy also. This is we know from the simple harmonic oscillation from the classical mechanics, that the total energy of the harmonic oscillator has kinetic energy and the potential energy. Now we can write it in different way. Here m is the mass and v is the velocity, but we can write it in terms of momentum. If we write the kinetic energy in terms of momentum, then it becomes p square by 2m. Similarly, k in case of spring, it's a spring constant, but this is a constant of the oscillation. We can write it half k x square, this term, as half m omega x square. Here the omega equals root over k by m is the angular frequency of the oscillation. Now, in quantum mechanics, to solve the problem, we first need to construct the Hamiltonian. Then we solve the Schrodinger equation to get the wave function for the system. Then using the wave function, we can get all the other informations or extract all the other informations for the system. Now, keeping in mind that this is the total energy of the harmonic oscillator, we can write the Hamiltonian for the quantum harmonic oscillator in this way, where h hat represents the Hamiltonian, p hat is the momentum operator. So this is p hat square by 2m, this is the kinetic energy operator, and half m omega x hat square is the potential energy operator. So the potential energy operator would be Vx is this one. Now we want to solve this problem, that is, we want to solve the Schrodinger equation for this Hamiltonian to get the wave function. But as you can see that the momentum operator here, the the kinetic energy operator p square by 2m involve second derivative, because if you remember that the momentum operator p would be minus I squared d by dx. So the kinetic energy operator, kinetic energy operator is h square by 2m d square by d x square. Now you can clearly see that this term involves second order differential equation or second order derivative. Now to solve the Schrodinger equation for this Hamiltonian, which would be simply like this, h hat psi equals E psi, or E would be the energy of the quantum harmonic oscillator, we have to solve a second order differential equation because h hat involves second order derivative. But this is difficult. So we want to simplify our life. Actually, the quantum harmonic oscillator problem can be solved in two ways. One, you can do this. This involves the polynomials and all the other techniques, and it's time consuming and complicated. Rather, we can simplify the Hamiltonian, and which we call the factorizing the Hamiltonian, such that the equation that we need to solve involves only first order derivative. So instead of solving the second order differential equation, we can solve the first order differential equation to get the wave function for the quantum harmonic oscillator. But for that, we need to manipulate the Hamiltonian or rewrite the Hamiltonian in a way so that we can get to the first order differential equation. So in this today's lecture, we will show how to factorize the Hamiltonian and how to solve the quantum harmonic oscillator algebraically so that it involves only the first order differential equation. So now this is the Hamiltonian. So if we take half m omega square out and we write it like this, so now you can clearly see that this one is a square of a square term, and this is also a square term. So the things in the parentheses just look like this one, a square plus b square. So if we want to factorize this one using the complex number, we can write it this way. So here this is I is the imaginary number, a minus ib is the complex number, and a plus ib is also a complex number, but this is the complex conjugate of this one, or vice versa. So we like to this way. So let's but there is one problem, because a and b are number. We can exchange their order in their multiplication, but x hat and p hat are operators, and we know that they do not commute. We know that the x hat commutator between x hat and p hat is equals I h cat. So they do not commute. If they would commute, then it would be 0. But instead of 0, we have I h cat. So they do not commute. That means that we cannot exchange their order. We have to keep in mind in multiplication their order. So this for that, it may involve some extra terms. So just let's try to know it. So we start with writing like this way. So this is the Hermitian conjugate or complex conjugate of this term. And then, so we go with this multiplication. Now see what the results are. So we have x hat multiplied with x hat. We have x hat square. We have this term minus I p hat by m omega multiplied with I p hat by m omega. We have I square minus, and the I square is minus 1. So I square equals minus 1. So with this minus, it becomes plus finally. That is minus I square is plus 1. So we have p square by m square omega square from these two terms. Now the cross terms. So if we multiply this one with this one, then we have this term I by m omega multiplied with x hat p hat minus the other cross term, that is this term multiplied with x hat. So we have this. Now we can write x hat p hat minus p hat x hat as commutator, and we know that the result of the commutator is I h cut. So I h cut multiplies with I gives you minus h cut. So from this term, these two, the product of these two terms, we have these terms. Now you can clearly see from the Hamiltonian, this is what we have in the Hamiltonian here. But we have an additional term when we factorize this term. So we write the Hamiltonian. Before writing the Hamiltonian, let's redefine these terms. So we write this term to be a hat. So this term would be a hat dagger. This is the Hermitian conjugate of or complex conjugate of this term. But they are a hat is not Hermitian because they are not same. So you can see a hat is not equals a hat dagger. They are not Hermitian, but this is the conjugate of this term. So we write it like this, two terms, Hermitian conjugate and this. Now the Hamiltonian becomes Hamiltonian has this term. So this term would be like this one. But you can clearly see that a hat dagger a hat is Hermitian, because if you take the Hermitian conjugate of this one, a hat dagger a hat, then we take the Hermitian conjugate. We know that the order will be changed. This one will come first here. So in that case, and it will, the Hermitian conjugate of this will be written and then this one will go next, but the Hermitian conjugate of the Hermitian conjugate is same as the original one. So so this would be, so therefore we can see that this is Hermitian, but A and A hat are not Hermitian, but this product is Hermitian. So the Hamiltonian becomes like this, which is Hermitian. So, and this is just a number. So it just gives us, or it just depends on the definition of the ground state. So we can see that another Hamiltonian is this term plus some additional number. But we have achieved what we wanted to achieve. We have factorized the Hamiltonian, and we can see that it also satisfies the condition that the Hamiltonian has to be Hermitian, because A hat dagger A hat is Hermitian. Now, let's calculate the commutator of these two. And if we, what we did, if we just do the multiplication, or say, let's just see, since x hat commute, the commutator between them is 0, and the p hat commute with p hat, the commutator between them is 0. So we will have only the cross terms. That is that x hat with this term. Similarly, this momentum term with the x hat. So, so let me see what I did. Yes. So this is what we did. So just like this. Now we know that x hat, the commutator between x hat, p hat is equals I squared. So p hat x hat would be minus I squared. Now if we put the values and simplify, we have this one, 2 squared by m omega. Now let's rescale this so that we have the commutator, result of the commutator is 1 only. That's simple. So we write it like this way, then we will have the commutator result. The commutator is 1. So what we did, we multiplied the square root of this with these two terms. Now let's redefine this one to be A, which is called annihilation operator. We will get to know soon why it is called the annihilation operator, and its Hermitian conjugate is a dagger, that is called creation operator, and the commutator between these two operators is 1. So now with this creation and annihilation operators, if we write them as write them in terms of position and momentum operator, we will have these two equations, and we can see from here that this is not, this operator is not Hermitian. That is, they are not, they do not represent any physical variables. But if we solve these two, we can get x hat and p hat, which we know that has to be Hermitian, and we can check it here easily. So if we take the Hermitian conjugate of this one, this is become A hat dagger, and this is become A hat. This is same. If we take the Hermitian conjugate of the momentum, then here we have I. This become minus I. This becomes A hat dagger. This is A hat. But this minus, if we take into account, then we end up with the same term again. That is the condition that the position operator and the momentum operators are Hermitian is satisfied. Now, in terms of the creation and annihilation operator, the momentum operator is, Hamiltonian operator is simply like this. So this is now a simple, the very simple look Hamiltonian. So this is the advantage. After factorizing, we get a very simple term. And this term, that A hat dagger, A hat, is called the number operator. It is because when this operates on the wave function, it gives it gives a number simply. What this number represents, we will get to learn it in future lectures, inshallah. So now what we can see from here, So just to remind you that this A hat and A hat dagger are these two terms. What we have here that the Hamiltonian operator is involves the number operator plus some number. So that means that what will be the eigenstate of the number operator will be the eigenstate of the Hamiltonian and vice versa. So if the number operator gives an eigenvalue n, then the Hamiltonian which gives the eigenvalue as the energy would satisfy this equation. So that means that if we know the eigenvalue of the number operator, we immediately know the total energy, that is the eigenvalue of the Hamiltonian. So this even further simplifies our task. So for any wave function, we only need to know that what the number operator gives, that is what is the eigenvalue for the number operator for that particular wave function. Once we get the eigenvalue, we get the energy. Okay, now since we have factorized the Hamiltonian, we want to find out the ground state wave function for the quantum harmonic oscillator, and we also want to calculate the energy of that state. So now let's take the expectation value or calculate the expectation value of the Hamiltonian for the wave function psi, which we assume to be a normalized state. We are not saying yet this is the ground state, this can be any state, but we are saying that this is normalized state so that we have the expectation value of the Hamiltonian operator is written like this way. Now we know that the Hamiltonian operator involves that this number operator, that is A hat dagger A hat. If we write them, so this becomes two terms. One involves this A hat dagger A, and another is simply a number, because we know that since we have assumed this is normalized, the inner product of psi is 1. So what we will have, we can now we can take this operator here. So if we take them, the dagger will be simply the A. So there's a Hermitian conjugate we have to take. So the Hermitian conjugate of A dagger is simply A. So this is what we did. Now this is as I said, this will be 1. So we have half h cat omega. Now, if we see that this is a wave function, this is a wave function. The inner product of two wave function is always greater or equal 0. It is 0 if the wave function is 0. If the wave function is not 0, then the product is a positive number. That is, the lowest value of this product can be 0. So the lowest value of these two terms, sum of these two terms, can only be half h cat omega, because the lowest value of this could be 0. And if we have a higher value, that is some positive numbers. That can be integer, that can be something else. We're not worried about that now. But so what we understand from here, the lowest energy for this expectation value of this Hamiltonian would be half h cat omega. Now we can only have this. We can only have this. So if we have A psi equals 0, remember, in that case, the inner product of this equals 0, then we have this energy. So if we write this way, the Schrodinger equation which we want to solve, then it will have the lowest energy value, which is half h cat omega, and the energies will be this half h cat omega or greater than. So this could be any wave function. For any wave function psi, then it will be, we are not saying that this is A psi is 0. It can be anything. But if it is 0, then this is half h cat omega. But if it is not 0, then the energy is greater than half h cat omega. So we can say that to get the lowest energy, we have to have a state which satisfies this equation. A hat psi equals 0. Let's call this state is the ground state, because it has the lowest possible energy. And the energy would be, of course, half h cat omega. So now we know that how A hat we have defined. So if we write A hat, the total description of the A hat, then we have this one. Then this is a constant term. We can get rid of it. And we know that P hat equals minus I a squared. I have written it before, minus I a squared dy dx. So then we have this term. Now you can see this is a first order differential equation. By solving this first order differential equation, we can easily get the wave function psi, the ground state wave function. Whereas at the beginning we have seen that Hamiltonian involves second order differential equation, but if we wanted to do it without factorizing, we had to solve the second order differential equation. Now, after this algebra, we only need to solve the first order differential equation to get the solution of the, or to get the wave function of the ground state quantum harmonic oscillator. Now you can see from here easily the differential equation, differentiation of psi 0 involves also the variable x. So the result would be simply an exponential. This is the term, the result, and this is the normalization factor. You can do it yourself. I'm not going to do it. This is for the students as a homework. So this is the ground state wave function for the quantum harmonic oscillator. And since we assume this one, that is this would be 0. So from here, we say that the lowest energy, that is the ground state energy, would be half a squared omega. So this is the ground state energy, and this is the ground state wave function. Now you can see that we have solved the quantum harmonic oscillator for ground state after doing some algebra, factorizing the Hamiltonian. Then we solve the first order differential equation. Now, just what we said before, that the n hat is a number operator. What we get if n hat operates on the wave function, because we also said that once we know the eigenvalue for the n hat, we know the energy immediately. So let's see if we can solve this, or we can get the energy from this way also. So we know that a psi 0 equals 0. So if n hat operates on psi 0, what will it give? It will give 0, because n hat is a hat dagger a hat, but this term is 0. So the result is 0. That is, we can write n hat psi 0 equals 0 multiplied with psi 0. So the eigenvalue of n hat is equals to 0 for the ground state wave function. So then in that case, we have the ground state energy equals E0 half h squared, h squared omega plus h squared omega into 0 plus half, because this is the eigenvalue of the number operator when it operates on the ground state wave function. So we can get the energy also by operating number operator on the wave function, and this is all. So just to summarize, we have factorized the Hamiltonian. We have written this way, where a hat and a dagger are these terms. They are not Hermitian, and the ground state wave function has this solution. We have solved a first order differential equation to get the ground state wave function, and the ground state energy would be half h squared omega. That's all for today. Thank you.